that's all for the announcements. And now to Alannah to introduce our speaker.
So thanks so much, Charles, and a huge thanks to Isabelle Chambefort for joining us today on All Deposits Hub. So yeah, like Charles said, my name is Alannah Brett, and I'll be co-hosting today. But first, I'd like to introduce Isabelle. So Isabelle's research centers on the magmatic hydrothermal geochemical transition in hydrothermal systems and volcanic arcs. Currently, Isabelle is a senior geothermal geoscientist at GNS Science at the Wairakei Research Centre in New Zealand. Now, before delving into the geothermal world at GNS in 2010, Isabelle was focused on the metal side of hydrothermal systems with a postdoc with John Dillis working on the Yanacocha epithermal high sulfidation cluster and source of sulfur and magma, and also at CODES on the Olympic Dam deposit. And all of this was on a solid basis of her PhD at the University of Geneva on high sulfidation systems in Bulgaria. So Isabelle, as your career path explored both the geothermal and epithermal deposits and the metals and high temperature fluids in these systems, we really look forward to the insights at this crossover of perspectives within the hydrothermal realm today. So thanks again for joining us. And now I'd like to pass the virtual floor over to you.
Well, thank you very much. Kia ora, everyone. Good evening, good morning. It's the evening in New Zealand. Thank you so much for the invitation. It's a great pleasure to give a talk to the All Deposits Hub today. It took me a little bit back to think a little bit more again about metal and particularly the implication that what we can learn from active systems such as what we have in New Zealand. So today I'm going to present a series of observations and facts that are not necessarily just mine. And I will use a lot of the work of some of my colleagues here in New Zealand, particularly Julie Rowland and Stuart Simmons, that have been diving in the world of metal transport in those geothermal systems for years. So just wanted to acknowledge all of them. And obviously all of this work is in collaboration with my colleague at GNS Science and other collaborators worldwide. So just to get back into what drives hydrothermal system, that they are fossil or they are active. Hydrothermal system just related to hot water circulating in the crust that can, because of the high cation, can dissolve some metals. And so you have basically a control from a and it's a worldwide thing where you have the geodynamic, the magmatism, the structures, and the basement that play a massive role in characterizing hydrothermalism. So keep that in mind when every time we're arriving on an environment where there is a potential for metal deposition, all of these different aspects has to play a role. And so if you're looking specifically in Volcanic Arc, where we found most of the magmatic hydrothermal system, which are the biggest probably copper and gold reserve on Earth as well, they are located where you have the Volcanic Arc, around the ring of fire, the arc of, obviously everybody knows the Chilean belt and in US, also the Tethys belt and Japan, Philippines, and obviously New Zealand. And when you're looking where the high geothermal systems are right now, we're actually not that different. Those high systems, those arc, the ring of fire, the US, Chile, Peru, they play a massive role in understanding heat transfer around in the crust, if you want. So what the parallel that I want to put here is that those hydrothermal systems are quite similar, and active is just an expression. We just do not have the time lapse to have generally the metal precipitation of the economic value, if you want a bit, but we can learn a lot from studying active systems around the world that are right now drilled for energy purposes. So we're going to dive into this little island here, the North Island of New Zealand, because it's an amazing natural laboratory, and we're very fortunate here to have this in our backyard. New Zealand is at the junction of the Pacific Plate and the Australian Plate, and the North Island of New Zealand is characterized by the subduction of the Pacific Plate underneath the Australian Plate. And in the South Island, you have this large dextral strike-slip fault system that is known as the Alpine Fault. And then in the south of New Zealand, the subduction orientation change, where you have the Australian plate subducting underneath the Pacific plate. Another characteristic of the North Island complexity is the subduction of the Ikurangi Plateau, which is an oceanic plateau that is literally dragged and subducted underneath the North Island, creating a very complex subduction area, and is blocked in the south at this transition zone. The whole subduction is kind of blocked here. The whole thing migrated, so the magnetism, the volcanic arc migrated from 20 million years for the North Island towards where this current position here in the central Taupo Volcanic Zone located here. And as an expression of the evolution of the arc system, you also have the evolution from a fossil to an active hydrothermal environment, where you have the fossil core mantle environment that, if for the people that were following, have seen Julie Rowland on the YouTube or the Visit Hub, she talks a lot as well about the implication of the core mantle gold deposit here in Hawaii. But today we're going to focus in this particular area, where most of the geothermal system generate a lot of heat and are utilized to generate electricity. So the Taupo Volcanic Zone is a vast natural energy source, and we have over 23 high temperature geothermal fields. That means that there is some water in 23 places in the crust, at shallow crust, that have been interpreted to be over 220 degrees C. We utilize 7 geothermal fields for generating electricity, plus some direct use associated with these heat resources. And the maximum temperature that was measured is in Rotokawa at 3 kilometers, and it was around 340 degrees C. So pretty hot in the crust in New Zealand for sure. So the Taupo Volcanic Zone is named because it's one of the most active volcanic areas on the planet. And in the last 2 million years, generated at least a minimum of 6,000 cubic kilometers of rhyolitic caldera event. And this is not accounting for the domes or any pyroclastic associated with the domes. So the volume of magnetism, of volcanism associated with the Taupo Volcanic Zone is equivalent to Yellowstone. And we're still finding some new indiumbrite associated with that. The rifting, the volcanism started 2 million years ago, and and the silicic volcanism started, for what we know, at 1.8 million years ago. So a very productive, very active area with 8 recognized caldera, but currently 2 volcanic centers that have most recent caldera in the last 40,000 years. The Okatana caldera, located in the north near Rotorua, and the Taupo Volcanic Center, which is basically where I am right now. And the geothermal system are located on the arc front. Most of the high temperature are located in the arc front, but you will notice that the Taupo Volcanic Zone is defined as well by a very extensional setting, where there is what we call the Taupo fault belt, associated with a lot of active faulting in certain places that are literally pulling apart the crust. There's the extension in the northeast of the Taupo Volcanic Zone is around 50 millimeters per year, and around 7 in the southern part. So it's a rifting arc, and most of the heat output is located in the forearc, but not where you have most of the active fault. It's located in the alignment with the arc system. So we're going to dive a little bit in the Taupo Volcanic Zone. So if we're looking at cross-section, that is cutting through basically what do we know around the Taupo Volcanic Zone. And that's, please forgive me, it's a little bit schematic, but what we need to know is that the Taupo Volcanic Zone is quite exceptional, because in the south and in the north, you have a normal arc volcanism with the Tongariro National Park and Rapehu volcano, which are andesitic cone building system, White Island in the north that separate basically the continental crust, and the Kermadec arc that continue in the Pacific Ocean. But the central Taupo Volcanic Zone is associated with an extreme volume of basalt and mafic magma underplating underneath that and associated with an extension that create an intense magmatism and therefore an intense heat transfer in the crust. And as most of you will know, it rains quite a bit in New Zealand, so not that much, but a little bit. And so this extensional, the amount of volcanism and the high heat really enhance the hydrothermal activity. And so we have deep hydrothermal cell going down in the crust and generating geothermal system at the surface. Here we go. So that's basically when you're looking at where we thought about the structure of an hydrothermal system, and the first paper that came on, the definition of adularia elite or low sulfidation epithermal system. The structure of it hasn't changed that much since in Decanley and Ellis in 1983, where you have a deep heat source, a rising plume of hot fluid transported at surface. When you're getting close to the surface, you're getting the two-phase fluid boiling, so a boiling zone, where you have some zone of condensations, steam heated, acid sulfate melt put at the surface. And that's where most of the time you're getting some mineralization, gold, silver, arsenic, antimony, mercury deposition above the boiling zone. And that is the standard model that is utilized for adularia elite or low sulfidation epithermal exploration in nowadays, and it's very relevant in the Taupo Volcanic Zone as well in our geothermal system. So it's really the base, the knowledge that we learn from those geothermal systems has been feeding the ore depositor community for a long time as well. This is something new. In terms of the Taupo Volcanic Zone, there's few gold prospects that have been drilled, but nothing really economic. As you could see, there's, 1 meter, 10 meter of 2 grain per gold, which is the best occurrence in our quarry, but nothing really that is economic, that is drilled for mineral resources. The best resources that we have are probably in the geothermal fluids. And this is a scaling inside of this inside of one of the Ohaki geothermal well, where you have this amazing, beautiful silica scaling. So this is amorphous silica favor that are they're gray because they are loaded with sulfide and other precious metal. So very rich in copper, tellurium, antimony, arsenic. All of those goodies are trapped into those wells. And it's a problem for the geothermal industry, but for the mineral deposit community, there's been a wealth of information coming from those scale. So if you would dive a little bit more now into the fluid composition, what do we know about the geothermal system? So there is 2 types of composition in the fluid, and both are related to the high or low gas content. So you have the high gas content that are aligned with the arc front, and that's a system such as Rotokawa, Ohaki, Karo, that have a low chlorine in the liquid, high nitrogen argon, high boron chlorine. And they have, and so those are the one in red here. And you have the low gas content, Warake, Mokai, Rotorua, Waiotapu, which have low carbon dioxide, but a high chlorine liquid. When I'm talking about high chlorine, they're still dilute near neutral pH fluid with a chlorine content around varying from the low, from the high chlorine from around 2000 ppm to 1000 ppm, 900 ppm chlorine. So we're not talking hypersaline brine here. There's still very dilute fluid. There's also a lot of sulfur that can come out. So to give you an idea, for example, this is at Rotokawa, there is more or less a flux of 48 tons a day of H2S, no SO2 coming at the surface in any of the geothermal system in the central Taupo Volcanic Zone, which is very different to the Arc which like, for example, in White Island, obviously in period of quiet moment, where you have around 25 tons a day. So there is actually as much CO2, H2S coming from those geothermal systems as there is for any other volcano. So if you want, we need to start thinking about the Taupo Volcanic Zone as the equivalent of a supervolcano, as a degassing, a breathing hydrothermal system. And that can form, for example, a cluster of epithermal deposit. In terms of analysis of metals, so the work of Kevin Brown and Stuart Simmons over the years have been quite exemplary in analyzing some of the fluid. So they collected sample down in the well, in the reservoir, trap it, and analyze for metal content. And so we know there are metals in those fluids because they are precipitating at the surface. And here, one of a clear example, which is Champagne Pool, where you have those distinct orange sulfur-rich precipitate that contain very high concentration of heavy metals, particularly arsenic and antimony, that gives this beautiful orange color. And you have, as you can see, a 3000 ppm chlorine for a medium acidic pH. But downhole, we have the same thing, where you have some systems that are quite enriched in silver and gold, and some of them, such as Rotokawa, are quite enriched in tellurium, or Mokai enriched in copper for that instance. So there's a lot of evidence that you can form an ore deposit based on the flux of metal that are fluxing toward in the fluid. And we dig a little bit about some of it in the rest of this talk. But one of the things that I want to discuss today with you, and I do not have an answer, it's really an open discussion here, is Stuart's proposed that the high concentration of silver, gold, and tellurium in Rotokawa and Mokai are attributed to direct fluid inputs from intrusion of andesitic or basaltic magmas, respectively. And we're going to challenge a little bit this. I do not have necessarily an answer. I just want to challenge this a little bit. So what do we know about the geothermal system? So we are lucky enough to have a lot of wells that have been drilled. And so we can learn about the stratigraphy and what, even if we can't, we don't have an open pit or an underground mine, we'll still have a lot of drilling and we can reconstruct and date the stratigraphy, very classic. And so if you're looking at a high gas system, such as Rotokawa, we're going to dive a little bit into Rotokawa. In the north, the system Natamaiki here. And Natamaiki is quite an example. There is a fossil intrusion that has a hydrothermal alteration halo. And so we can reconstruct what will be the pattern for degassing, andesitic intrusion, tonalite to andesite intrusion underneath the Taupo Volcanic Zone. And this was 500,000 years ago. So if we look a little bit of what will be the zoning above the intrusion, it's very classic, and you will recognize the typical zoning that you will have above a porphyry copper, although sub-economic here, where you have, an acid, deep hypogenic acidic alteration with andesite, pyrophyllite, some topaz mineralization, and an enrichment toward the surface in gold, silver, arsenic, antimony again, and an enrichment in lead, zinc, bismuth closer to the intrusion. But if we're looking at a site such as Rotokawa, which is currently the high gas active hydrothermal system, so we have here, this is the hydrothermal alteration zoning where you have the dispersion of chloride. So here you have this well here, RK8 is basically this one here. So that's the same cross-section projection, RK21. This well here is this one here. So you can basically, that's more or less the projection of the hydrothermal alteration. You can see some of the temperature here that are reported as well. So we can really easily reconstruct the hydrothermal alteration pattern with the temperature measure and analyze in area of the well. So which is definitely an advantage compared to ore deposit, which we have the temperature. So we have this typical zoning with adularia, elite at depths, and some evidence of chalcedony and obviously chlorite mineralization. So Rotokawa geothermal system, and I want to dive a little bit into Rotokawa. The reason is because it's one of the highest gold and silver tellurium flux in the Taupo Volcanic Zone. So my colleague Ted Bertrand, who is looking at magnetotelluric and imaging. So magnetotelluric create they interpret magnetotelluric data, and they are able to put forward both imaging and model of the conductivity in the crust. So those conductivity can be due to electric conductivity, can be due to fluid phase, to magmatic hypersaline brine, or to magmas. And there is a beautiful magnetotelluric anomaly underneath Rotokawa that clearly show an hydrothermal plume with that reach 3.5 kilometer, where you have and they interpret that there is a zone of partial melt underneath Rotokawa at around 4.5 kilometer, basically a shallow intrusion. And if there is present, there is the solved hypersaline brine and gas will be expected to accumulate underneath that zone. So based on these beautiful geophysical images, we've been trying to apply some of the chemical vectoring that is done regularly in the ore deposit in order to target mineralization in porphyry copper, to try to see if we could reconstruct the same kind of dispersion pattern above this suspected intrusion. Obviously, we do not have any drilling that's go that as deep as 4.5 kilometers. So we are expecting. So this is, for example, of the sample that we've been analyzing, and we are going down. You see up to almost 3 kilometers. The sample have been taken with an in equilibrium with temperature almost up to 350 degrees. And we're going to look at Rotokawa. We did the same for Oaxaca in the north, which has the same deep connectivity zone underneath. And we're going to compare with some of the Natamaki fossil hydrothermal systems that are clearly linked to magmatic hydrothermal transition. So this is, for example, the dispersion of some of the sample we have, where you have all the wells drilled that are utilized to generate electricity. So they're taking the fluid, but we've been looking at the rock. And as you can see here, this is the volume model of the magnetotelluric anomaly. And we have some wells that really clearly intercept those high conductivity modeled area. So we've been looking particularly at some of the sample to see if we can see any trace metal dispersion in the system. And so this is what and I'm not going to go in detail of every element, but in green here are the increase in some elements that you find in the fossil hydrothermal system. And in blue, it's the Oaxaca geothermal field, and in red, it's the Rotokawa geothermal field. One interesting thing is the total absence of silver for Rotokawa or Oaxaca compared to a magmatic hydrothermal system where you have an enrichment. We clearly see an increase in arsenic and antimony or gold toward the surface, particularly at Oaxaca, which has been observed in the part by Stuart Simmons. But most of the time, most of the enrichment, particularly if you're looking at Rotokawa, the mineralization is going straight to the surface and is really enriched in both at the surface, in both mud pool, basically. And so you have the same here, you have the antimony, and you're jumping 3 order of magnitude where you're having mineral precipitation in the mud pool. One key thing that we did not find is an increase in that we observed in for some of the geothermal system is an increase in some metals. Here, as well as a model of the dispersion in metal, in gold for the system. So for some of you may be familiar with the dispersion that is observed generally, and there's the work by Scott Halley, John Dillis, and Dick Tosdall on the zoning above the gassing magmatic fluid and porphyry copper system when you're having all the zoning in alteration, and you can basically track down the enrichment in disbursement due to the hydrothermal alteration, the enrichment in certain metal as you're going away and you're reacting your magmatic fluid with your host rock. So we can observe the same type of zoning above Natamariki magmatic hydrothermal system, where you're getting an enrichment in copper, moly, tin, selenium, and even tellurium. But in the geothermal system, in the high gas geothermal system, you have a very high arsenic, antimony, gold, sulfur, and mercury zoning, as well as lithium toward the surface. But basically what you're lacking is all the chlorine complex metals. So you do not have any evidence, we do not have right now in the whole rock, remember this is a whole rock, I'm not talking about reservoir fluids, but in the whole rock, we do not have dispersion of those chlorine complex metals that are generally associated with hypersaline brine and chlorine degassing from magmatic system. So from that observation, we are having a problem where the geophysics is telling us that we have this beautiful hydrothermal plumes, and that needs to be explained, obviously. And you have, but we do not find any chemical evidence dispersed in the rock of any magmatic degassing associated with that, as well as any evidence of high temperature acidic hydrothermal alteration that will be associated with a magmatic degassing. So if you want, that will be your typical schematic representation of a shallow intrusion, where you have the dispersional pattern associated with your magmatic fluid, where like in the Taupo Volcanic Zone, you have a magmatic match between 6 and 8 kilometers, and you have structure that definitely trigger the hot plume towards the surface and creating an enrichment, but we're missing this connection with the shallow intrusion from a chemical point of view. So as for going back a little bit into this hypothesis about that those high silver and high gold content in the Taupo Volcanic Zone are associated with andesitic magmatism and arc system. What we know is that there's no evidence of andesitic magmatism. It's a rifting in the central division. It's a rifting, rhyolitic dominated arc where there is a lot of endoplasmic basalt and you have a large volume of rhyolite. So even if you had a shallow rhyolite, you will have degassing of chlorine, most likely, particularly if it's cooling down. So what we're having actually, it's evidence for arc type degassing, where you have an enrichment in arc dominated, such as the nitrogen fluids, a high CO2, but we do not have the evidence of arc magmatism in base of what we're observing in our deposit as a chlorine complex and chlorine degassing system. So to dive a little bit, we have been doing some work on the source of where the most of those metals that reach the surface are, the gold, copper, gold, silver, and other arsenic, antimony. They're dominantly sulfur complex in those environments. And so you need to find a source for the sulfur to be able to transport your gold system. And so we've been looking at what is the story of the magmatic sulfur. Can we have sulfur reaching the surface at for greater depths? An interesting fact, so we've been looking at melt inclusion record. This is the record for Oronuria, which is basically what will be the magmatic system pre-formation of Lake Taupo. And here it's the melt volatile content in ppm, and it's in terms of the percentage proportion of sulfur, fluorine, and chlorine. And as you can see, you're losing the sulfur as soon as the base of your crystal merge. You're diminishing the sulfur. So you have the basalt that have around 2000 ppm in sulfur. As soon as you're reaching here, which are already rhyolitic melt inclusion composition, you do not have any more sulfur. Your sulfur is lost in the system by magnetite precipitation due to magnetite event, obviously some sulfide precipitation, but there is less magmatic phase. You do have a little bit of, obviously, as soon as before the large eruption, where you have saturation of the vapor phase, there is a little bit of sulfur. And considering the large volume, that's enough to generate a sulfur peak during the eruption. But you need to have the high volume, those large silicic magma creating to have this vapor saturation, to have this exsolution of volatile. In the present condition right now in the Taupo Volcanic Zone, there's no evidence of a shallow, at 4 kilometers of a shallow high silica rhyolitic melt-dominated body that will be saturated in a vapor phase. So your sulfur is basically trapped in the mineralogy in the mesh. In the mesh. So there is this conundrum where you need sulfur to reach the surface, and you have sulfur deep in the crust, but you're losing it in between. And that's a little bit the same thing with some of the chlorine. You do not have, so we don't have chlorine complex. We don't have sulfur coming from the magma. So we try to test another source for the metal content in the Taupo Volcanic Zone geothermal system. And so this is a work that we've been doing with my colleague Bruce Montaigne in the experimental geochemistry lab. So if you're looking at the different source of sulfur and chlorine, you may have a heat source, which is the deep geothermal system. Those are in ppm, so you have high chlorine and a low total sulfur. You have a gray waki that have quite a bit of sulfur in it. You have some young volcanics that have some high copper chlorine and some low, obviously a low sulfur total in the volcanic rocks. And obviously you have an enrichment toward the surface in sulfur, and you recycled everything. So what we've been doing some continuous one-pass flow through simulation. So we're reacting in a pressure vessel. We're reacting some of crushed rocks, fragment of rock that are clean and sieved, and we're reacting them for, as you can see here, 80 days, and we are increasing the pressure and temperature. And we've been doing this from 25, so ambient temperature, to 400 degrees. And the reason we did that is we wanted to understand at one point, and if we could, release some of the chlorine and some of the sulfur just by reacting the rock with some water. And this is what we observe. So here, the Taupo pumice, basically, we're reacting some chlorine-rich pumice. And you can see that as soon as you're reaching 250 degrees, we have a huge peak in chlorine. And every time you're increasing, you're cracking a little bit your rock, releasing again more chlorine as you're reacting your rock. We also, during this experiment, you're creating a lot of hydrothermal alteration and total alteration of your glass. But you're generating a total at the end, you having around 1600 milligram per kilogram, so 1600 ppm of chlorine in your fluid at the end of the experiment. And for the same thing, we're reacting the Waipapa, which is the gray waki, which is the basement underneath some of the geothermal system in the Taupo Volcanic Zone. And what you can see here is that as soon as you're reaching 300 degrees, you have this huge release in sulfide that is associated with the destabilization of pyrite in the sedimentary, the metasedimentary gray waki. So it's quite interesting. And you can generate it around 600 ppm of sulfur just by reacting the rock with the basement rock in the geothermal system, as long as you have the heat. And we do have the heat because there is enough magma. So one aspect of that is that if you're taking the volcanic basement interface, and if you're looking at the temperature, when you're reaching, basically when you're going to interact, so in yellow here are your pumice, which will be your volcanic sedimentary cover, and in green, that will be your basement. So if you have a small volcanic cover, you will release, as you're increasing temperature, as your fluid is coming down to your geothermal system and reaching 400 degrees, you're going to have a huge sulfur chlorine ratio. But as you're going down, if you have a higher proportion of volcanics, and you're still reacting quite a bit with your greywacke here, you're lowering your chlorine until you are inversing basically. And when you have a high depth or high thickness of volcanics, you will devolatilize your pumice a lot. So you're having a high chlorine content in your fluid, where like you're barely going to react with the greywacke, and so you're releasing less sulfur. So, and when you're thinking in terms of transport of metal, the implication of having variation in your sulfur chlorine ratio in your fluid, it is quite important. And so that may explain some of the variation we are seeing in terms of chemistry of a geothermal fluid. It's just a matter of water-rock interaction and heat from magmas, obviously. So just for your consideration, and this is really to trigger a little bit the discussion, obviously, is when you look at some of this greywacke, there is beautiful rhomboidal sedimentary pyrites that have been analyzed in the south, very close to the Macraes mine, and those are quite enriched in metals such as gold, silver, tellurium. So I'll let you think on that, what could be the source of a metal in those geothermal systems. So in conclusion, basically, so as for any ore deposits, mineral precipitation in geothermal system is dependent on the transported position mechanism. Fluids are enriched and enough metal flows through the system to generate epithermal mineralization with time. So we definitely know that there is enough metals in the system. But I will say that the source of metal, and it's still debated if it's magmatic or not, basically. I hope you have some question. Kia ora, and thank you very much.
But before we get on to questions from the audience, we do have a guest panelist with us today. And that is Professor Laren Diamond, who's a professor at the University of Bern in Switzerland. And he's worked extensively on hydrothermal systems, and we've invited him today to open up the discussion. He's also from New Zealand, like myself, so has quite an attachment to these systems. And yeah, I'd like to invite Laren if he has any questions to start us off today.
Sure. Thanks a lot, Alannah. That was an excellent talk, Isabelle.
Thank you.
You're so fortunate to have so much information, so many different kinds of data. And like you said, that's a huge advantage over just near surface sampling that most explorationists are working with. So I noticed in those beautiful cross sections that the isotherms, which you've reconstructed, present day temperatures, actually cross-cut a lot of the mineral zonation boundaries. So although you said you've got the mineral alteration temperatures nailed because you can observe the current temperatures, in fact, there is discordancy. And so I'm wondering how we're looking at a snapshot of this big system. You know? It's evolving through time. It's very young. What do you think is happening? Is the system growing, evolving? And that's why we're having this discordancy between temperatures, or is it decaying, dying? What's your take on that?
I'm gonna put it back for the people. Hopefully I can. No, that's not that. That's not gonna work. If I go this like that. Sorry, that's not very elegant. That's this one, right? Yeah, so that's actually very interesting. So my colleague Mark Simpson has been working on this, and obviously the paper is not submitted because it's entirely my fault. So I'm taking this on board. It can go on YouTube. So yes, you're entirely correct. This and this has been quite revealing. And what we've been discovering is that there is likely a cooling of the geothermal system. So the northern part of the Rotokawa geothermal system used to be hotter in the past. And it's likely associated, from Mark works, it's likely associated to some of the hydrothermal events that happened like around 25,000 years. and that refocus the hydrothermal fluids. So you can have variation in that amount of time. You know, we're talking 50,000 to 100,000 years. We're not talking 2 million years here. But the other thing as well that we've been doing, and at some work with John Dilles that we did both together that I didn't present today, we've been looking at the elite chemistry. And we've been doing, particularly because we can compare where you're getting the elite chemistry in the potassium in the elite with the measured temperature. And so you kind of have a temperature, but those temperature boundary that we put, you know, elite precipitate start crystallizing at, 220 degrees or something like that. There is actually a plus and minus, and that's going to be quite variable in function of the rock you have. So a system like Rotokawa, which has a huge andesitic derived greywacke and an andesitic on top, your elite has a lot of chloritic substitution and over, there's a lot of chlorite. So you don't have actually a proper, like from a stoichiometry point of view, you don't have a very nice mineralization of the elite. And so your temperature, your elite does not reflect the temperature, measured temperature as well. But there is as well a cooling effect. So we can decipher with fluid inclusion work, with obviously the measured temperature, we can really assess when you have a cooling. And it's a matter of, 10,000 years. That's really very fast time in terms of mineral deposition, basically.
Okay, thanks. Yeah, perhaps there are some other questions from our listeners.
Yeah, thanks, Leon, for starting us off with that. I think there's kind of a kind of follow-up one. Siant, I hope I've pronounced your name right. If you'd like to unmute, you're welcome to ask your question.
So I spent about 5 to 6 years exploring the Taupo Volcanic Zone for epithermal gold mineralization, and was around when Henley and Henquist were at GNS. And I suppose we developed a view from an exploration perspective that we thought geothermal systems actually evolved over time. And our evidence for that was when we go to places like the Waihi Gold Mine or Mueller's Reef. Mueller's Reef is in the Central Volcanic Zone, and the Waihi is the old arc. You can see episodic mineralization in the veining texture. And so we were of a view that not only did you need a geothermal system, you needed a geothermal system that was somehow being refreshed. And our argument or thought process at the time, and this is 20 years ago, was that potentially we were getting magmatic coming in into the arc and refreshing magma chambers, and we were getting magmatic gas fluxes, but they didn't last very long. And so the bulk of the record is not a mineralizing event. And then every now and then you'll get a release event, and you'll have a nice little quartz vein that's full of gold and silver. And that's what you see at the Waihi Gold Mine. You see it Mueller's Reef only had one event, and Oakuri also only had one event. I mean, you can crawl all over the abutments. There's lots of little quartz veins there, but you never see a cross-cutting event. So it was a one-shot mineralizing event. So we thought, our epithermal geothermal system had to evolve over time. And if it didn't refresh and you didn't have new input, you got a prospect and you didn't get a mine.
So that's maybe what's happening in the Taupo Volcanic Zone right now. Yes, there's several aspects to that. There's one thing that I should have mentioned is that I still have to see any vein in any of the geothermal system, like a proper mineral vein with gold in it. So that's one of the things that we haven't intercepted. And the reason is, and Julie Rowland and Stuart have been discussing that a lot, is actually the depth of the water table and the fault control. So you do not have the best condition to form vein right now in the TVZ, because you have a disseminated permeable fluid circulation instead of a focus point for your boiling to occur. So that's the first thing.
So I would actually agree with that, which is why
Good.
with the exploration company I was with, I said, you need to leave the Taupo Volcanic Zone, because all those pyroclastics, they're too permeable and porous, and you're never going to get the system to focus. And I think at Oahu Broadlands, Stuart Simmons or one of the researchers found that there's actually 3 upflow zones over its history. And for an epithermal person looking for a gold mine, that's a killer.
Yeah, I don't know if it's a killer or not, but you definitely do not have the good condition. The other thing that I was going to say in terms of magmatic pulses, think about the Wairiki geothermal system that is literally 10 kilometers, not even north of Taupo. Wairiki, there's evidence of past hydrothermal alteration in the last 100,000 years. In that period of time, you created the caldera volcano. You had a massive flux of magma heat and magma coming at the surface. You probably had a lot of magmatic degassing. None of that is recorded in the geothermal system as far as we know. So we're looking a little bit into this. So there's clearly, even if you had some magmatic events, some of this structure that control the geothermal system have been independent on some of this large silicic system, which large of magmatic pulses. So we don't have as well some the same kind of record history that you will have in vein system like in Waihi. Because we just don't see those veins, and it's really hard to get the record of any possible magmatic pulses in the TVZ right now. I've been trying to look at some sulfur isotope in the past, and it's still not very clear if you had any clear sulfur or any chlorine peak associated with that. So we're having some work doing now on oxygen isotope in Tohara geothermal field to see if we can see the onset of the caldera volcano, the Taupo volcano, which when you're thinking about the size of this eruption, and we're talking super volcano here, we're talking a large amount of rhyolite, the gas rich in chlorine, rich in sulfur, and we can't see that 10 kilometers away in the geothermal system. So it's really very interesting. But yes, in terms of mineral and gold deposition, we do not have the best condition right now in the Taupo Volcanic Zone. In terms of fluid condition, that may be fluid composition, that's a different thing. So I'm not sure if I answer, but hopefully I give you some comments.
Yeah, you did answer, because one of the things that sort of drove us crazy was that Wairiki, we couldn't pick up any gold or that much gold or silver in the geothermal precipitates. Yet across the river at Rotokawa, if you go and sample the muds of the Rotokawa, Lake Rotokawa, there's 3 to 5 grams of gold sitting in the bottom of that lake. And why two geothermal systems, metal transport should be so different over such a short distance.
Yeah. Yeah, still puzzling me. 10 years I've been working on the system. I'm still puzzled about this question. Don't get me wrong. I'm still working on that.
No worries. And just a final comment. I am a geologist who worked at the Macraes gold mine, and we absolutely think all of our gold at that mine has come out of the grey wackies that were subducted underneath there.
Yeah.
And it is a very large deposit.
Yes, it is. Yeah.
I don't know how many places in the world you can walk 6 kilometers along continuous gold mineralization. We've shifted 1 billion tons of it.
Thanks very much for your questions and the really insightful comments from working in the field there, Sant. yeah, I'd like to open, if anyone else does have any other questions, we've still got 5 or so minutes, so you can put them in the chat. Also, Lauren, if you have any others, you're welcome to jump in there. I do have one myself, and I guess it's kind of linked to what we were just discussing at the end there, the spatial variations. I mean, at the beginning you said like there's 23 geothermal fields and areas of the fluids going on, and I wonder how much it varies really between all those different fields. We already saw quite some variations between Rotokawa and the other ones we discussed today. So I wonder if you just comment a bit more on that.
Yeah, no, I fully agree. I mean, it's very puzzled. So here we go. So that's what we were talking about earlier. So Waraki, Rotokawa, oh my gosh, I do not have a scale on there. Wait, I can't see it. That's terrible. Anyway, there is like 10K. That's literally, it's really next to each other. There's nothing that's separate, right? Rotokawa, you have a high gas system, 900 ppm, more or less, chlorine in the fluid, high CO2 flux, 400 ton a day. It's like high sulfur flux. There's tons of metals in the mud of the surface. Krupp and Seward, Terry Seward has been working on that, and metal transport. There's a lot of metals, really rich, a lot of tellurium in the system. Waikiki, barely anything. And we are right there. The biggest difference is Rotokawa. So that's what you align with. There's several points. Rotokawa is aligned with the arc. So that's where you're getting probably some of this, and that's where you're getting some of this deep arc degassing. So the nitrogen, nitrogen coming out, this high CO2 are coming from that place. Rotokawa is hosted, the reservoir is a large pile of andesite from the onset of the Taupo Volcanic Zone. There is an onset of andesitic magmatism that happened at 2 million years. And it's at the border of the rift where there is the gray wacky. So you have a big portion of the fluid that is actually based in the gray wacky as well, which is in that particular place, it's granitic derived. It's not andesitic derived, but it is granitic derived. The Waikiki system, we haven't found the bottom yet. Waikiki is hosted in a buried piecemeal caldera, which was called the Whakamaru caldera, which was a big volcanic event at 350,000 years ago. And that created a succession of collapse filled with ignimbrite and other rhyolitic andesite and other things like that. So that's where I was discussing, in the influence of your recharge, basically, where you're getting your volcanic pile versus your gray wacky pile, that can influence basically where the variation in chemistry you're observing. Waikiki, the deepest well must be something around 3.2 kilometer. We're still in ignimbrite. We're still in silicic rock. We haven't found any evidence of the basement yet. So it's telling you like that could be some of this. That could be some of the explanation. Obviously, it's really hard to assess if there is the same heat source, therefore the same magnetic source, if there's variation in where you're degassing it. You're very close. When you're thinking in terms of, if we have a big silicic batholith, which are, the size of, 5 cubic kilometer for a shallow intrusion, but bigger than that for a batholith, like a proper rhyolitic batholith, they're huge, right? If you get a cupola that is enriched, that may be enough to focus some of the fluid where here you don't have it. But I mean, I quite like actually the fact that you may have both, you need both the magmatic fluid to bring some CO2, to bring some of the, arc gases towards the surface. Obviously the heat, we need the magma, there's no other question over that. But the role of the gray wacky, the role of the Rotokawa andesite in that particular field, I think we still have a lot to learn on that. And so we're continuing working, but it's only in places like that where we can really piecemeal, little detail, little rock. You don't necessarily have that luxury in when you're looking at a ore deposit, because you don't have all those variation. We're assuming one event, and And here we have as I said, we have a 300,000 years resolution. That's more or less when we're thinking the TVZ, the tectonic system, it's 350,000 years, the current situation that we have now. So yeah, I mean, that's one of the reasons that can explain some of those variation. Could be just effectively like shallow degassing, and there's just not chlorine coming at the surface, or just trickle that doesn't bring any metal. But my porphyry copper background and colleagues and other, we're like, where is the magma? It's just a little bit like that, because I'm used to seeing, some evidence, and there's no evidence in fluid inclusion as well. There's nothing that shows any hypersaline fluid or anything like that in any other system. I don't know if I answered your question, Alannah.
Yeah, you did. That's great. Thanks for the insights. It's excellent. And we've got quite a few comments in the chat there from people. Isabelle, I can always save those for you and send them to you afterwards. Charles or Laren, do you have any final comments?
Yeah, I just have one desperate question. Has Bruce Mountain measured the metals in those flow-through experiments?
We are in the process of doing it. So we are looking at those metals. They are very low. We need low detection, as you can imagine. Yeah. So yes, we are definitely in the process of looking at the metals in this. Okay. So yeah, there is some leaching of rare earth from the Greywacke. And there's a proceeding coming up in the New Zealand Geothermal workshop by my colleague Lucien Zakowski that is working with us in the team. But yeah, so the metals is definitely we should see them. Let's just put it that way. If you're leaching pyrites are never just sulfur and iron. There's always a little bit of things coming with it. Is it enough to form the deposition we have in some of the system? We need to do a proper mass flux for that. Once we have the value.
Good. Okay. Work in progress. Looking forward to seeing it then. Thank you.
Thank you.
Thanks very much. Thanks, Laren, for joining us. Charles, one final one.
Question. Considering that COP26 is ongoing, I have to ask something regarding emissions. A few years ago, I was at a conference where there was some preliminary data which suggest that rift systems emit significantly more CO2 than we previously thought. However, nothing really came out of that afterwards. I was just wondering, as you've been working with these for a significant time, in these high CO2 systems, do you have any measurement of what sort of the emission rate of the CO2 is?
I should have not give you that talk today. I should have given you the other one. So I've been working quite a bit on emission. So that's part of some of the work I've been doing. So there is, because we need to understand the emission. Yes, indeed, there is some emission. So a system like Oaki or Rotokawa have a little bit significant emission. One thing that is not taking into account when they're reporting some of the emission at the power station is the emission from the field itself. So you're not gonna, it's volcanoes. So even if you are not utilizing any geothermal system, you're still going to have CO2 degassing. So as part of the legislation in New Zealand, we are targeting a 100% renewable by 2030 and 2050 carbon zero. And geothermal has been flagged that it is part of the renewable, but they have to do something about the emission. And so the industry is clearly looking at a solution. So there is already some testing that's going to happen to re-inject the CO2. So not only re-injecting, we are re-injecting some of fluid to maintain the pressure, but they are looking at how to capture the CO2, putting it back in the system as well. But that doesn't come without some chemistry issue, as you can imagine, when you are cooling down your CO2. In terms of, there's also some capture and having greenhouses on the line. And so there's a lot of work that is going in that space right now. In terms of the volume of emission, we recently calculated the volume of emission. What did I say? The minimum estimate that we have right now for the natural degassing of the central TVZ is around, and that's minimum because we haven't finished doing the flux for all the field, It's around 4,000 tons a day of CO2 that is released in the atmosphere by the volcanic area. And the emission from the geothermal system will account, from the power station, it's half of that. So even if you are stopping utilizing, you're still going to have a lot of CO2 degassing naturally from this massive volcanic area. So there's a lot of communication that needs to happen also in that space. And as we're starting to re-inject the CO2, what we've been observing, so what's happening as well is that by the utilization of a geothermal system have been depressurizing quite a bit your system. So you're losing your emission have been decreasing as well. So we're decreasing the emission. But if we are starting re-injecting some CO2 into the reservoir, we're going to see an increase in the emission actually. So it's going to be like a cycle. So all of this modelings are going on right now. This is the one priority for the geothermal industry in New Zealand because they know, and they've been very active on that. They know that if so New Zealand does not allow any more exploration for oil field, for example. So they know that if they're not finding a solution for their emission, they're going to become the next dirty energy industry, and they definitely don't want that to happen. They want to keep the green renewable, stickers. And I'm definitely looking for that. And that's some of the work as well that we've been doing into exploring for the supercritical, because in supercritical condition you may have less CO2 actually because you have less dense material. So it's and less total dissolved solid. So that's all of this thing, yeah. Sorry, I'm like suddenly you realize the other part of what of the work I've been doing as well.
Brilliant, thank you.